Hello, this is Jerry Pinter. Welcome to Chapter 6. In this first part of the lecture, we will be studying the kinematics of uniform circular motion. Chapter 6 is broken up into 3 parts. In this part, we will be doing the kinematics of uniform circular motion. In Part 2, we will be looking at the dynamics of uniform circular motion. And Part 3 covers gravity and orbits. So let's start by imagining an experiment or a demonstration here where you take a light ball, like a tennis ball, and attach it to a short string, about 1 meter long, and you twirl it around and around over your head. So this is the view from above, a bird's eye view of the situation, and the ball is just going around and around. Here we can see in our animation showing the motion kind of slowed down in slow motion. So this is an example of uniform circular motion. That's an object that moves with constant speed along a circular path. And uniform circular motion is basically a special type of motion that we are covering in this course. But there are many, many examples and applications of uniform circular motion. And so that's why we have almost an entire chapter dedicated to it. So in this first part of the lecture and Part 2 as well, we will be looking at many different applications and examples and situations where we deal with uniform circular motion. The way to describe uniform circular motion, obviously, you know, the object is going in a circle, but notice the radius of the circle is just the distance from the center of the circle out to where the object is, and the radius is going to remain constant in uniform circular motion. And also notice the velocity vector is tangent to the circle, meaning the velocity is always pointing forward along the motion of the object that's rotating. So there are 3 things we can start off with here to characterize uniform circular motion. And these are just the very basics of uniform circular motion. The first is called the period. Period is the time it takes an object to make 1 revolution. So for example, if we were to start right here and just count how many seconds it takes this object to go all the way around until it gets back right here, that was 1 period. The frequency is the number of revolutions or cycles per second. And the frequency and period are always related by a reciprocal relationship. So the frequency is 1 over the period. Likewise, the period t is 1 over the frequency. So notice we're using an uppercase t to designate the period so that we don't confuse it with the time variable, which is usually a lowercase t. And then frequency, we will use the letter f for number of revolutions or cycles per second. By the way, the units here are also called a hertz, H-E-R-T-Z. The speed of the object, obviously this object is moving. It's covering a certain amount of distance per unit time. That's the definition of speed. So one way we can characterize its speed very simply is by just taking the distance as 1 complete revolution around the circle. So that's the circumference of the circle. That's how much distance it covers during 1 period. So the speed of an object in uniform circular motion is given by 2 pi r, that's the circumference, divided by uppercase t, which is the period. And since t, remember, is 1 over the frequency, by inverting this relationship right here, we also have another equivalent expression for speed. The speed is equal to 2 pi times the frequency times the radius. When we dealt with kinematics of objects moving in a straight line, it made sense to talk about the position of the object in terms of meters or distance. For an object moving in a circular motion, basically the object never gets anywhere because it's just going around and around. So it's more convenient to talk about an object's angular position when it moves around in a circle. So an angular position is a convenient way to specify where an object is on a circle. The angle theta is usually defined using the x-axis. So here is our object here, and you can think of this object is going around in a circle, something like this. So we've drawn here a coordinate system, an XY coordinate system, with the origin right at the center of the circle. So our object, remember, this is its radius here. This is the radius of the circle. This distance over here, this arc of the circle, is called the arc length, which is given by the letter S. Okay, and we'll be talking about these relationships in the next couple of slides. What we're mainly concerned with here is the angular position. So we measure an object's position on the circle by its angle theta. And notice we're measuring it with respect to the x-axis here. Okay, so in this picture right here, it looks like our object has an angular position of something like 45 degrees. So regarding angular position, we can measure angles using two types of units, degrees and radians. So you've certainly heard about degrees before. You used a protractor, for example, in your geometry class to measure an angle in degrees. We are going to often be using radians to measure angular positions for circular motion. It's much more convenient. So a radian is defined as there are 2 pi radians, which is abbreviated rad, R-A-D, in a full circle. And a right angle is therefore pi over 2 radians, okay? Because a right angle is 1/4 of a full circle. 90 degrees is 1/4 of 360 degrees. Pi, of course, is the famous number, 3.14159, and it keeps on going from there. So, you know, the question comes up, why do we want to use radians? Why should we confuse ourselves with another unit of angle when we've already got degrees? Degrees, we understand there are 360 degrees in a full circle, and a right angle is 90 degrees, and so forth. Well, this is the reason. A radian measurement is defined, so in other words, theta in the units of radians is defined as the ratio of arc length S over the radius R. So remember, here is our object here, up here. All right, it's a radius R from the center of the circle. This length here that it's basically traveled along this arc length S is a distance. So the ratio of this distance S to this distance R gives us how many radians theta is. So we can always easily calculate this angle theta in radians if we know what this arc length is and what the radius is. So this relationship here, theta equals S over R, is usually written without a fraction as S equals R theta. So arc length is just equal to the radius times the angle measured in radians. Okay, so furthermore, the number of radians in a full circle, remember, is equal to S over R, but the arc length, if we're going to talk about a full circle going all the way around the circle like this, then the arc length is equal to the circumference of the circle, which is 2 pi r. And of course, 2 pi r divided by r, the r's cancel, so that tells us that the number of radians in a full circle is 2 pi radians. So there are 2 pi radians in a full circle, just like there are 360 degrees in a full circle. Occasionally, we will have to convert back and forth between radians and degrees. That's easy to do. 1 radian, we just multiply it by 360 degrees per 2 pi radians, because 360 is a full circle, so is 2 pi radians. So if we take 360 and divide it by 2 times pi, we get the conversion factor. 1 radian is about 57.3 degrees. Now that we know how to specify an angular position using either degrees or radians, the next step in kinematics is to define displacements and velocities. So when we talk about motion in a straight line, remember a displacement was just how far the object actually traveled in meters. Well, now what we're going to talk about is an angular displacement. In other words, how many angles I'm sorry, how many radians did the object move through when it moved? And likewise, we're going to talk about velocity. For an object moving in a straight line, velocity was just how many meters per second. But now we're going to talk about how many radians per second the object moves. So let's take these in order. The first one is displacement. If we talk about position, all right, the change in position, especially if we're talking about along the arc of a circle, since we're dealing with circular motion, the change in position here is given by the final position minus initial position. That's how we always calculate a delta. So for an angular displacement, we're finding the change in angular position. So delta theta is described as the final angle, theta sub f, minus the initial angle, theta sub I. So look at this picture here. Let's imagine our object starts here and it moves in along a circle here, along a circular arc over here to our final position. All right, so this is, if you were to measure this arc here, this would be delta S. That's the distance that it moved in meters. But what we're often more interested in is what was the change in angle of our object. So this angle right here is delta theta. That is our final angle, which would be this angle from here down to here, minus our initial angle, theta I, right here. So delta theta is the change in angular position. Just like velocity is the rate of change in position, so velocity is equal to delta S over delta T, where delta S is just a length in meters. Now we're going to talk about something called angular velocity, which is the rate of change in angular position. So angular velocity is given by the symbol omega. All right, this is the Greek letter omega, a lowercase omega, and it's defined as the angular displacement divided by the time interval. All right. Now there's, I realize this is a new equation for us right here, but really it's the same equation as this velocity if we just make the following substitutions. We replace regular velocity v with angular velocity omega. We replace s, displacement, remember that was up here, with theta, which is our angular position. So this equation basically is the same form as this one. We're just now dealing with the change in an angle theta, not in a change in a position. So angular velocity has the units of radians per second. It basically tells us, omega tells us how many radians per second is this object moving, all right? How many radians per second does it undergo as it's going around in this circle? So this slide shows us several useful relationships between velocity, angular velocity, and what's called frequency. So I'm not going to go through the steps to derive or prove these relationships because it just takes up a little bit of our time here. You're welcome to go through the steps if you want to. But the first relationship that we end up proving here is the following. Regular velocity in meters per second is equal to the angular velocity, omega, times the radius of the circle. So this is a very basic, fundamental, and simple result here, where if we know one, we can always get to the other. So in other words, if we know what omega is, and obviously we would have to know the radius of the circle, we can figure out how fast the object's going. Likewise, if we know the speed of the object and we know the radius of the circle, we can solve for omega and figure out what the angular velocity would be in radians per second. We can do some more useful relationships. Again, the proof is shown in these steps here, which I'll skip, but omega, which is the angular velocity, is related to the frequency. Remember, frequency is revolutions per second. How many times per second the object is going around in a circle. They are related by the factor of 2 pi. So omega is equal to 2 pi f. All right, and furthermore, remember that f is equal to 1 over the period. So by plugging that in and solving for period, the period of revolution is equal to 2 pi over omega. So these are formulas that you probably are not going to memorize, especially right off the bat. After you use them a while, they may stick in your head. But these are ones that we would definitely want to just keep note of, and we'll use these to help us solve some problems. By the way, the angular velocity omega is also sometimes called the angular frequency. However, this textbook doesn't use that terminology. So as is always the case in physics, the real way to make sure we know and understand the physics is to solve problems with it. So let's go ahead and take a look at an example which has 5 questions with it. So our situation here, we're given a fan blade in an electric fan, and it's rotating at 300 RPMs. Now there's a new unit for us. An RPM is a revolution per minute. So that means this fan blade is spinning around 300 times every minute. And we're also told that the radius of the fan blade from the center out to the tip is 20 centimeters. So let's just go through a bunch of questions here that will use most of the formulas and equations that we've already seen in this part of the lecture. So the first question is, what is the rotation frequency and period? All right, so remember, frequency is units of revolutions per second. We are given the number of revolutions per minute, so we have to do some conversion here. So the frequency is 300 revolutions per minute, that's RPMs, and then we have to multiply by 1 minute per 60 seconds. That will get our minutes to cancel, leaving revolutions per second. So 300 divided by 60, you can do that in your head, is 5. So the frequency here is 5 revolutions per second. The next question was, what is the period of revolution? Well, the period, remember, is 1 over the frequency. So we have 1 over 5 revolutions per second. That's 0.2 seconds per revolution. In other words, it takes the fan blade 0.2 seconds to go around one time. Part number 2 here. What is the blade's angular velocity? So here there are 2 ways to do it. The easy way to do it is just to use the equation from the previous slide. Omega equals 2 pi f, all right? And f, remember, we've solved it right here, is 5 revolutions per second. So I have 2 times pi times 5, which is 31.4 radians per second. Another way to do it, which is perfectly fine and good, it's maybe a little more lengthy, is we can take omega, we can write it as the frequency in RPM. So we have 300 revolutions per minute. Convert that to seconds by multiplying by 1 minute over 60 seconds. That cancels the minutes. Now we've got revolutions per second. And then we have to multiply by the fact that there are 2 pi radians per revolution. So this revolution here, rev, cancels this rev down here. And all that's left then is radians on top and seconds on the bottom. So I have 300 divided by 60 times 2 pi, and that will give us the same answer of 31.4 radians per second. Obviously, this method up here is more convenient and efficient to do, less work for us. All right, let's move on to number 3. What is the velocity of the outer tip of the fan blade? So again, we're going to resort to and refer to our equation from the previous slide. Velocity equals r times omega. R is 0.2 meters, right? Remember, this is in centimeters, so we convert that to meters. We know omega is 31.4 radians per second, and so we end up with 6.28 meters per second. Now, some of you might be wondering about the units here. What happened to this radian here? We've got meters here divided by seconds, and that's all I show here. What happened to the units of radians? Well, this is kind of interesting. The radian has no units. It's unitless. And the reason for this is, remember how we can define radians. Radians is an arc length divided by the radius. So arc length is in meters, it's a distance. And the radius is in meters, it's also a distance. So the units of radians is meters over meters. And of course, the meters cancel, leaving us with no units. So radians is technically a unitless unit. It doesn't carry any units with it. So oftentimes they are not included in our final answer, especially here we're solving for velocity. So our units are meters per second. Okay, let's move on. Number 4, what is the angular displacement of the blades in 2 seconds? So we're trying to figure out how many radians do these blades turn in 2 seconds. So here's where we use our kinematics equations. Remember that omega is defined as delta theta over delta t. So therefore, delta theta is equal to omega times delta t. I'm just rearranging our equation for omega. So this is the same as saying distance is equal to velocity times time. Now we're talking about not a displacement in distance, but a displacement in radians, in angle. So our answer is 31.4 radians per second multiplied by the time, 2 seconds, and 31.4 times 2 is 62.8. And here the seconds cancel and we're left with radians. That is our angular displacement. Let's see, next question. How long does it take the blades to rotate 90 degrees? So let's do 2 things here. Let's first figure out what our displacement is. Well, 90 degrees is a quarter of a circle. So what we're gonna do here is, there's 2 ways to do this. The short way is you can just think of, all right, a full circle is 2 pi radians, and we need to turn 90 degrees, which is a quarter of a circle. So 1/4 of 2 pi is 1/2 pi, or pi over 2. More formal way to do it is to start with 90 degrees and convert that to radians by multiplying by 2 pi radians divided by 360 degrees. And what we get here then is 90 times 2 times pi divided by 360 will give us pi over 2. So that's not our answer to our question. That's just how far it moves. The displacement is pi over 2 radians. The time here, we're again going to use the same equation here for our omega. Omega is delta theta over delta t. So delta t is equal to delta theta over omega. So we have pi over 2 radians is our displacement, divided by omega is 31.4 radians per second, and that gives us 0.05 seconds. Let's return to our kind of thought experiment here of taking a ball on a string and twirling it around over our head like this. Remember, this is kind of bird's eye view looking down from above. And let's imagine this ball is twirling around and around like this at a constant speed. So the ball's not speeding up or slowing down. So it doesn't appear to be accelerating, but it actually is. The reason it's accelerating is because the velocity of the ball is changing direction continuously. It's not changing its speed, but remember, velocity is a vector, and vectors have 2 things. They have magnitude and direction. So the magnitude of the velocity vector does not change. That's just the speed of the ball, but the direction is changing, obviously. So this is a new type of acceleration for us, which is called centripetal acceleration. And centripetal acceleration literally means center seeking. So the direction of the acceleration is towards the center of the circle. And one way to sort of visualize this is, remember from chapters 4 and 5, we learned about Newton's second law, F equals ma. And we learned that whenever there's a net force on an object, the object will accelerate in that direction. So if we think about our tennis ball here, right, our tennis ball is feeling this string tension pulling it in the direction of the center of the circle. So no matter where the ball is on this circle, it's always being pulled towards the center. That's the tension direction. So the acceleration is always in the same direction as the net force, right? F equals ma is a vector equation. Whatever direction the force is, the acceleration points the same direction. So this is called centripetal acceleration because the acceleration is pointing in the same direction as the force of the string, and that is towards the center of the circle. So again, centripetal means center seeking, and the way to calculate centripetal acceleration is given by this formula here. It's v squared over r. So in other words, if we know the speed of the ball, v, we just square it and divide it by the radius of the circle. Likewise, we can remember that we can say that v is equal to omega times r, and plug that in here, and remember to square everything, and it simplifies to centripetal acceleration is also equal to omega squared times r. So depending on whether we know v or omega, we can use either of these equations to quickly calculate centripetal acceleration. It's kind of interesting and not that difficult to prove or derive our result for centripetal acceleration, that A is equal to v squared over r. But again, I'm going to, in order to keep the video lecture here short, and I'm not going to go through the steps here or do the proof, but if you're interested, you can follow the steps here and see how we prove or derive this result. The important thing for us is just this result here. Centripetal acceleration is equal to v squared over r, or centripetal acceleration is equal to omega squared times r. Here's a conceptual quiz to test your knowledge of some of these concepts that we've learned in this lecture so far. So this is a bird's eye view again, looking down on a toy merry-go-round in the playground. And we've got two kids here. Jacob is in this position here, and Emma is over here, and this thing is turning around as they play on the ride. So there's three questions here that I want you to think about. Which child, Jacob or Emma, is moving the fastest? Which child has the largest angular velocity? And which child has the larger acceleration? So go ahead and pause the video and see if you can come up with answers to these problems, and we'll discuss them shortly. So the first question is, which child is moving the fastest? Well, we can do this without really even thinking about any of the formulas or equations. Remember that they're both going to travel all the way around the circle in the same amount of time. But Emma, because she's farther from the center of the circle, she's going to travel a farther distance in the same amount of time, because Emma's basically going to go and follow this, I'm tracing out her path right out here. This is a larger circle. Compared to Jacob, he's just going to go around this small circle in here. So Emma covers more distance in the same time, therefore she is going faster. The equation that shows this is that, remember, the velocity of an object is equal to the angular speed or angular velocity omega times the radius. Well, they both have the same angular velocity. In fact, that's the second question here. Which child has the largest angular velocity? Well, neither. They're the same. They are both going around the circle with the same number of radians per second. Because remember, radians per second is measuring an angle, not a length or a distance. So their omega is the same, and therefore, since v is equal to omega r, Emma has a larger radius, so her velocity is going to be larger out here. Now, for the larger, who has the larger acceleration, the answer again is Emma, and the reason for this is most easily seen when we use the equation centripetal acceleration is equal to omega squared r. So they both have the same omega. It's no different between Jacob and Emma. But obviously Emma has a larger radius, so that means her acceleration is larger. Let's go ahead and look at a couple of quantitative examples with numbers in them for centripetal acceleration. So the first one here is, we'll consider this situation again where we're twirling the ball around our head on a string like this. Calculate the centripetal acceleration of a 0.1 kilogram ball swung around your head on a 1 meter string once per second. So, this ball is going to be going around something like this, right? Once per second. All right, so let's figure out the speed of the ball, because we need, in order to figure out centripetal acceleration, we're going to use v squared over r. So we need to know how fast the ball is going. So the speed of the ball remember, is, distance divided by time. So let's take our distance to be one complete trip around the circle. That's called the circumference, which is 2 pi r. And we divide that by the time, which is the period. And we were told that it's going around once per second. So we know the period is 1 second. Furthermore, the radius of the circle is 1 meter because the string is 1 meter long. So the distance from here to here is 1 meter. So our answer here for speed is 2 pi times 1 divided by 1. Well, that's just 2 pi. So our speed is 2 pi meters per second. That's something like 6.2 meters per second. Now we can calculate the centripetal acceleration. We can put 2 pi as our velocity, and we're going to square that number. And we're going to divide it again by the radius, r, which is 1 meter. So 2 pi squared turns out to be 39.5. And so our answer for our centripetal acceleration is 39.5 meters per second. By the way, just to kind of put some perspective in what this means, is remember the acceleration due to gravity is 9.8, which is around 10. So this acceleration here is almost 40. So it's about 4 times the acceleration due to gravity. In other words, we would say that the ball is experiencing 4 Gs, or approximately 4 Gs of acceleration. Now let's do a different one. Let's calculate the centripetal acceleration of the Earth as it orbits the Sun. Okay, so again, we're going to kind of do the same thing. We're going to use centripetal acceleration is v squared over r. So we need to find the speed of the Earth. So the speed of the Earth, again, is equal to the circumference of the circle, basically of Earth's orbit, divided by the time. So this picture helps explain the situation. Here's the Sun in the center of our solar system. The Earth is orbiting around the Sun in a roughly circular orbit. We're just going to assume it's a perfect circle here. All right, and so during 1 year, the Earth makes 1 trip around the Sun. So our circumference of the circle, 2 pi r, is going to be 2 pi times the radius. Now the radius of the Earth's orbit is about 93 million miles, but we need to convert that to meters. So I don't show how we do that here, but you can look that up. It's very simple to convert miles to meters. And you end up with 1.5 times 10 to the 11th meters. That's the radius. And what do we do with the time down here? Well, remember it takes 1 year for the Earth to go around the Sun. 1 year is 365 days, but we need to convert that to seconds. So we'd have to multiply 365 times 24 hours per day times 60 minutes per hour times 60 seconds per minute. So we have a bunch of numbers there. So the time in 1 year, the number of seconds in a year is 3.15 times 10 to the 7th seconds. So we have a couple big numbers here that are, one's dividing by the other. We're going to use our calculator and make sure we know how to use scientific notation and so forth. But when we do this calculation, we come up with the speed of the Earth is amazingly large. It's 30,000 meters per second. Okay, which is an extremely fast clip. So the Earth is flying around the Sun very fast. So you might expect, wow, we're going to get a really big centripetal acceleration, right, with that huge velocity. Well, the answer is surprising. And the reason is, first of all, remember we have to square the velocity. So 30,000 squared is even bigger. However, remember we're dividing by the radius. And the radius, again, I did it up here, is 1.5 times 10 to the 11th meters. The radius is huge in meters, okay? And so when you do the math here, this number up here divided by this number here turns out to be a very, very tiny number. The answer is 0.006 meters per second squared. This is nowhere even near 1 G, right? It's a tiny, tiny fraction of a G. In fact, it's so tiny that it's undetectable to us. We don't feel this acceleration as we're zipping around the Sun. Even though we're going 30,000 meters per second, the amount of acceleration is so tiny that we don't sense it at all.